So it's a pleasure to be giving this Meet a GERAD researcher talk. This is an initiative that goes back to the days where I was director of GERAD, and the idea was to sort of share research areas amongst researchers of GERAD and identify areas where the cross-pollination could take place. Hopefully this will go some way today in that direction. I'll be very pedagogical. That's the idea. So I'll stay away from too much mathematics as much as possible. So the outline of the presentation is I'll try to build up the ideas based on dynamic programming that lead to the theory of linear quadratic regulators. A very brief overview. This is classical material. But linear quadratic regulators are like the workhorse of optimal controls, applied optimal control. And they're pretty much for an OR crowd, which is what the GERAD is as a majority. They're really pretty much like what linear programming is for operations research. We will contrast operations research types of solutions to optimal control problems with that obtained from optimal control theory. Then I'll move on to the main core, the main subject of the talk, which is really mean field games, after a very brief review of what games are. And if we have time, we'll show an illustration in navigation, but mostly my goal is to present an application of mean field game theory in the control of loads in smart grids for better integration with renewable energy. So let's start with this dynamic programming idea in a deterministic context. First, when can you apply dynamic programming for optimizing some cost? Well, the system analyzed must have a so-called state equation. That is, the state is what you need to remember from the past and the present to forecast the future without any loss of information. And what we mean by any loss of information is that you're able to forecast future states. So it's a bit of a circular definition, but that's what the notion of a state is. What type of cost functions are admissible in dynamic programming? Well, the cost functions have to be additive and over time. And at each time, the cost must depend on the current state and the current decision. That's basically the setup for dynamic programming. Now, what's exactly the dynamic programming, so-called dynamic programming principle? It's a very, very simple idea, but which has profound consequences. And the idea is an optimal trajectory must remain optimal if the optimization problem is reconsidered at any time along the optimal trajectory. So to fix idea, let's think of this particular situation where you have an eagle trying to follow a prey. The eagle has constant velocity, but must adjust its angle all the time. And there's, a small prey that's moving at a constant velocity. So the eagle would like to adjust its angular position to meet the target after going through a minimal distance, which is equivalent to saying in minimum time. So what would the dynamic programming principle state in that particular case? Let's see. Well, the idea is if the eagle has computed some optimal path that gets it to the chick, to the prey in minimal time, the idea is if the eagle somewhere along the way started having some doubts that the path that it had computed earlier wasn't optimal, and from that particular position, which is at starting from t0, it went up to time t1, has reached position x1, y1 in space, in two-dimensional space. and then ask the question, well, what would be the optimal trajectory for the rest of the time? Well, the dynamic programming principle states that the trajectory must correspond exactly to the extension of the trajectory that would have been computed starting from the initial point x0, y0, t0. In other words, an optimal trajectory is optimal no matter where I start asking the question along a particular path of that optimal trajectory. So this suggests, in fact, that we could use dynamic programming as an embedding principle, which is going to tell us that, in fact, we need to be solving tinier problems than the big problem that the eagle was trying to solve. If starting from the final encounter time, capital T, if I back off to t minus delta t, where delta t is a small time increment backwards, the optimal optimal trajectory, the optimal decisions must be optimal, no matter what a point in the state space I am sitting at t minus delta t. So this means that for any state at t minus delta t, I have to compute an optimal decision, store that optimal decision associated with that particular state, as well as the cost associated with, because we call that the cost to go from t minus delta t to t. And then we back off to t minus 2 delta t, carry out exactly the same problem now, but we use the solution at t minus delta t as a building block. So from t minus 2 delta t, any state, I have to check what other state I have to move to at t minus delta t, so that when I add up the costs of moving from t minus 2 delta t to t minus delta t to that particular state, plus the optimal cost from there, I'm going to minimize my cost. Once I solve that problem, I have a new cost to go, a new one-step optimal decision, and I keep going backwards and backwards. And that's the idea of using dynamic programming. So you can see it's an algorithm that propagates from future back to the past. Future decisions are stored first, and then we slowly build until we backtrack all the way to the initial position, and then we have solved our problem. So that's an interesting numerical algorithm. It's also a global optimization approach, but it's computationally very hungry. It suffers from the so-called curse of dimensionality, because you don't know what the optimal path is going, which state it's going through. So you have to compute decisions for any state you are likely to go through over time. And that's very expensive. Now, how do we use the dynamic programming in optimal control? We make a different use of that principle. We use it to produce a partial differential equation called the dynamic programming equation, which allows us to characterize a necessary condition for optimality under condition of sufficient smoothness of the so-called value function. So the idea is the following. You have to start with a state equation. State equations are differential equations of first order. So you have a vector which can have as many as n components. The differential equations are the basis of physics and dynamics. All the laws of physics are based on differential equations. Then the derivative of vector x depends on x, depends on a set of controls that I can exert. This control can be scalar, vector, and so I have a vector of differential equation, which can be nonlinear in general, which depends on x, on u, and t. Now, we also characterize optimality by means of a cost functional, and typically it's an integral of a running cost over a control horizon from t0 to tf, initial to final, plus a final cost. And the optimal control problem is to find the control policy, U of t over time, within an admissible set of controls set on T0, Tf, which minimizes this integral cost. That's the optimal control problem. And when we apply the dynamic principle, the way to apply it is that, again, we're going to use this embedding principle, which is to say, I'm going to try to solve smaller problems, a family of smaller problems than the one I started out. So instead of starting from T0 to Tf, I'm going to start from a T, which is closer to the final horizon, try to solve that problem, record the solution, and then use that optimal control coupled with an optimal cost to build the solution for the larger problem. So, so we use an intermediary function, which is the optimal cost to go, also called the value function. So you start from any arbitrary state at time t, t within T0, Tf, and then you want to solve the integral costs and find the optimal policy from x towards the end of the interval. And the way we're going to get to the partial differential equation is we're going to consider two neighboring in time value functions at t and t plus delta t. So remember, we're working backwards. So we start with a optimal solution assumed at time t plus delta t. We state x of t plus delta t and try to reconstruct what j star of x of t and a time step delta t before, an interval of time delta t before, in terms of g star. When we do that, under enough smoothness conditions, we produce a necessary condition for optimality, which is a partial differential equation in the cost to go function or the value function, which involves derivative. J is a function of the state and time, j star. So the partial differential equation involves partial derivative with respect to time and partial derivative, the gradient of the value function with respect to the state, which we consider here as space. So it's like a space-time partial differential equation. And this partial differential equation involves a quantity which is called the Hamiltonian, which comes from, the name comes from mechanics. The Hamiltonian is a concatenation of the running cost in the under the integral, running cost function, plus what you can consider like a Lagrange multiplier, multiplying the state equation. So the vector on the right-hand side of the state equation, which describes the state dynamics, because this acts as a constraint. So this is really like an augmented cost, which is based on a Lagrange multiplier. But it turns out this Lagrange multiplier that OR people are familiar with, which is kind of what we call the shadow cost, it turns out to be the gradient of the value function with respect to space, the space vector. And so the dynamic programming equation takes this particular form in terms of the Hamiltonian. Now, what can we do with this dynamic programming equation if we apply it to a particular very important special case, which is that of a linear dynamics? So everything is linear in the state space, and the cost is quadratic. So the integral here is x transpose qx plus u transpose ru. This is a scalar, another scalar. So this is kind of like an inner product, if you will, except it's modified by a penalty matrix Q, another penalty matrix R, and there's also a penalty on the final state. These matrices are typically either semi-positive definite or positive definite, which results on costs which are constantly positive, and so or non-negative. So the costs are adding up over time, and what we're trying to do really is maintain the state close to zero. The reason being that this dynamic state model may be a linearized nonlinear model around the desired operating point. So you're trying to stay close to your operating point. And so when x is zero, you're on top of the operating point. So all along, you want to stay close to your operating point. You want to minimize the energy to do so. And it's very important at the final horizon, at the final time, to be really very, very close to your desired operating point. So typically, matrix M will correspond to a penalty which is higher than the ones associated with Q and R. And examples of running costs, for example, would be this cost for the running cost, and this would be for the final penalty. You can see the penalties on the states are much larger than on the running cost. This is because at the final time, you'd like to be very, very close to your desired operating point. And so if we apply the dynamic programming equation to that to that particular case, it turns out we can formulate a problem for which there is a closed form solution. Okay, so the way to write the partial differential equation of dynamic programming is to first try to express the optimal control in terms of the gradient of the value function by solving this optimization problem. So you optimize the Hamiltonian, which is that expression, considering that everything is fixed except u. So u is the only variable, and the other variables are all fixed. And it turns out that this is a convex function in u. So when you optimize this function, you're going to take a derivative with respect to a vector. There are standard ways of doing that. And it turns out that the optimal expression of the control is a function, a linear function of the gradient of the value of function at time t. So you substitute this expression in the dynamic programming equation, this expression, the u star in terms of jx, and you obtain finally an equation which depends only on the value function. It's a partial differential equation. It's nonlinear because it involves something like the square of the gradient of the value function. And in general, it would be very difficult to solve. But as it turns out, using the dynamic programming principle, we can start with the solution at the end of the horizon. If you're sitting at state x of tf, there's nothing to do. The optimal cost is given by this quadratic form. And if we hypothesize that the optimal cost to go will still remain a quadratic function of the state, but with a matrix K of t to be computed, it turns out that it will be possible to solve this dynamic programming equation, provided we can find a matrix which solves a matrix differential equation. It has to be solved backwards, starting from K of Tf equals M. M was the penalty matrix associated with the final state. It's solved backwards, and it's called a Riccati equation. Now, this Riccati equation has a long history. It started with the Bernoulli brothers in mathematical family in Switzerland in the 17th century, but then was studied closely by Count Jacopo Riccati in Italy in the 18th century, who solved special cases. And then it pops out all over science, this Riccati equation, very famous matrix equation. We know a lot about it. We know under what condition, sufficient condition for its solution, and it can be, we have numerical techniques to handle that. And the point is, once you solve that Riccati equation, you can express the optimal control. It turns out to be a closed form solution with a linear feedback in the state. Okay, so that's really the beauty of the linear quadratic regulator. We have a closed form solution. It's expressed as a feedback of the state, and we know how to compute that feedback function. And furthermore, there's a slight generalization of that problem, which is very useful in the control problems I'll be talking about, which is called the optimal linear tracking. That particular linear tracking problem is essentially you have a linear system, but you have also an output. So, for example, I may be interested in controlling the velocity of a car. And so the output is the velocity, and I'd like the velocity to follow the speed of the car to follow a certain desired trajectory. So the output is a linear function of the state, and instead of penalizing the state as we did in the standard linear quadratic problem, we're going to penalize the distance between the output and a desired trajectory r of t, which is predefined. So I have a target trajectory I'm trying to follow. I penalize the error, and I also want to minimize the energy to follow that target error, and I also have a final penalty. And using a dynamic programming equation, again, one can solve this problem in closed form. We're going to get a Riccati equation, which is the same as the one we had earlier. But on top of it, there's the optimal control is not only a linear feedback, it's affine in the states. It's a linear feedback in the state, but you have to add something called an open loop term, which depends on the target trajectory you're trying to follow, beta of t. And this term beta of t satisfies a linear differential equation once you have solved for k, because f of t is a linear function of k of t. So this becomes a linear differential equation, and it is solved backwards from a known initial condition. You can initialize that problem. So one can come up with a closed form analysis of this problem as well, and that's extremely useful. So this linear tracking problem becomes a building block for more complicated problems that we will be talking about in a short while. Now, are there any questions so far? Feel free to interrupt me if you think something is not clear at this stage. Okay, so I'd like to have a quick comparison for the sake of this OR-oriented crowd, which is the GERAD crowd. How would OR go about solving this problem? Of course, operations research may want to solve this optimal control problem. How would they do it? Well, they would not think of it as a dynamic system. They would think of it, they would think of the optimal control as being a sequence, a vector of decisions, which are indexed by time. So they will think of it as a single shot static optimization problem. So in one shot, I want to come up with what u at time 1 is, u at times 2 is, u at times 3, etc. So the solution will be a sequence of open loop control decisions. That is, at each time, I'm going to have only a single value of the control vector, not a family like a feedback law, but a single value. So no feedback laws. What does it mean? It means that the result I'm getting with respect to feedback is going to be very much dependent on the initial conditions that I studied for my optimization. So it's going to be extremely sensitive to perturbations along the trajectory. If something doesn't go as planned, I essentially have to solve things again from scratch. Okay, so very sensitive to perturbation. Instead, a feedback law is reactive. So even if there's a perturbation which takes me off course, I still have a feedback law. So it's robust against perturbation. So a feedback law is a solution to a very wide family of problems, and it's robust against perturbation. That's very important. In a static view, time is ignored. It's treated, the future is treated the same as present, and it's treated as a known quantity. And that's dangerous because in effect, I am taking, especially in a stochastic context, I am taking non-causal decisions. In other words, I'm assuming I know the future, whereas in fact, even airlines may have storms, may have strikes, may have all kinds of things. If I plan for the future on the basis of a deterministic future, then my decision is no longer valid, and I've been using the future as an input. Whereas optimal control, even in a stochastic case, the optimal controls will remain causal. In other words, the optimal control will produce a view of the future which is a prediction based only on the current observation and past observation. It's not assuming something that is not predictable. And finally, the problem with optimal controls, of course, is it handles constraints very poorly. So the limitations of this linear quadratic control is it doesn't like constraints, it breaks down under constraints, but by playing with the penalties and the cost functions, we can push the solution to inside the constraint set, and that's where OR can help tuning the parameters of a linear quadratic regulator problem. So now, having done this parallel with OR, let's move to the main subject today, which is mean field games, which is a tool actually for controlling large-scale systems. So let's say a word about games. What is game theory? Game theory studies situation of simultaneous optimizers. Previously, in optimal control, we had a single optimizer with a single cost. Here we have a collection of optimizers individually with individual costs. In non-cooperative games, we cannot talk about optimal control. The concept that replaces optimality is that of Nash equilibrium. Now, what's the Nash equilibrium? It's a situation which may be, by the way, uncomfortable, but nevertheless, it has some stability. It's a situation where any agent in the game cannot improve single-handedly through unilateral actions, cannot improve its situation. So if I am in that situations with everyone having settled on their decisions, if I were to change my decision, I would be losing. So because of that, somehow the agents sit in a sort of equilibrium, which can be happy, which can be unhappy also. It's called the Nash equilibrium. And games are typically very difficult to solve. Okay, even static games are very difficult to solve. But paradoxically, if you have games with enough symmetries amongst agents, so there's a lot of homogeneity and symmetry, computing Nash equilibria can become simpler, in fact, as the number of agents grows without bounds. That's not very intuitive. You're making the problem more complex. From a point of view of operations research, you're increasing the dimension of the system. At the same time, you're getting a simpler problem. This leads us to the analysis of so-called mean field games. And the best place to start developing an intuition as to what mean field games are is fish schools. Now, let's observe fish schools. They're fascinating objects that move in a very nimble way through time, where clearly every fish can be viewed as an agent trying to make decisions. Now, of course, in OR, if you were to control this fish school, the classical way to think of controlling the fish school is for some single central brain to look at every fish, observe their position, and then compute what the optimal decision of every fish is, and communicate it and recompute things over time. So that's a very computationally intensive and impractical, but unfortunately, even in smart grids, that's a way a lot of engineers are approaching the problem. Instead, we'd like to be able to reproduce the motion of the fish in an efficient way by thinking of every fish as being an agent playing a game. So let's see what kind of game the fish is trying to play. We can think of first the mass of the fish school by averaging the position of the fish over time. We can think of the red trajectory as being the centroidal trajectory, the center of gravity over time, okay? So we can think of this as being a known trajectory. Of course, it's not known initially, but let's think of it for now as being known. What should each fish do? Well, the agents, what they're trying to do is the fish are trying to remain close to the group, therefore close to the centroid. So we're going to penalize over time the error between their position and that of the centroidal position, which is assumed to be known at time t. But also, we're going to require the fish to track the centroid while minimizing the energy needed to do that. So by assuming linear dynamics for the fish, also we're going to make them stochastic, the results still hold because there's some stochasticity in the motion of the fish. Then we can formulate this as a linear quadratic game, a tracking game, where each fish is trying to follow the centroid. So why is it that as numbers grow, the game becomes simpler? Let's try to analyze the reason why linear quadratic minifier games become much simpler and are such a powerful practical paradigm. Well, the main reason is as numbers grow, laws of large numbers start to kick in. Why? Because in a game, when an agent changes its decision, the other agents immediately observe that and start changing their own position, and you get tit for tat, and it's very difficult to see where the group gets. However, if you have a very, very large group of agents which are doing something, 1,000,000 agents, and then the 1,000,001st agent tries to change its position, the group doesn't care what that 1,000,001st agent is doing. Therefore, we can think of the agents as becoming stochastically weakly coupled as the numbers grow. So a fish I and a fish j, arbitrary, are almost independent in their motion because the group is so large. As a result, the mean trajectory, which is the result of the averaging the trajectories of agents, will converge to a deterministic trajectory by the law of large numbers. It's unknown, but we know it's going to be some deterministic trajectory. So we can think now of an agent joining the group, and the agent will pick that trajectory, and it could solve a tractable linear quadratic tracking problem. It's tractable. I gave you the solution earlier. It involves solving Riccati equations and then linear differential equation. It's going to solve that problem, but the solution will depend on the x bar of t that the fish, the agent, has assumed. Now, how do I compute this x bar of t, since I had to assume it in the first place? Well, not any candidate trajectory is admissible because you need to have consistency. I have to assume a trajectory, x bar of t, such that if every fish optimizes, gives its best response to that trajectory, when I implement the optimal policies for all the fish, and I recompute their average dynamics, I should reproduce the x bar of t that I assumed in the first place when I carried out my optimal tracking calculation. This is the so-called fixed point calculation. We start with an x bar of t, we compute the optimal closed form solution, which is, by the way, decentralized. Every fish can compute it locally just on the basis of knowing its own position and some initial information. When the fish average their behavior, they have to come up with the same x bar. That's going to give you a system of equations which are mostly linear differential equations. And that's why And these linear differential equations have the same size as the state of the agent. In other words, essentially, or if you add the open loop equation, it's a bit bigger, but it's nothing like solving the game with a million agents, which would require a million times the size of every agent dynamics to solve coupled equations of that form. So it's a very powerful paradigm in the linear case. In the nonlinear case, you get partial differential equation. It's more difficult. So in the remaining time before that 35 minutes, I'm going to try to give you an example in navigation, which was published in 2011 with my PhD student Mujtaba Nourian and my colleagues Minnie Huang and Peter Keynes. Minnie's thesis was our PhD student. This is where we started studying mean field games for the first time. Now, it's well known that sardines, for example, like to move in circles to simulate a large fish, to scare off other fish from attacking them. Of course, it doesn't always work. Particularly birds will plunge and eat sardines. But the model, a very, very simple model, just a complete, toy model, is that we're going to assume we have leaders and followers in a population. All the fish have linear dynamics with some noise, Brownian motion, which simulates, stochastic motion of the fish. But we have cost functions for leaders and cost functions for followers. The cost function for the leader is different from that of the followers. The leaders have two objectives. They want to follow a predefined trajectory over time. For example, a circle. H of t is the trajectory of the circle. But at the same time, they want to make sure that the group remains cohesive. So the leaders, every leader wants to remain close to the mean position of the group of fish. So the mean position is the average, empirical average of the positions of all fish at any time t. And lambda is a coefficient between 0 and 1. So this is a convex combination, which could be, for example, 60% on the trajectory, 40% on the mean, depending on how you weigh, you prioritize cohesiveness versus the trajectory. And so the agents are solving a tracking problem, with this being the track trajectory. And it wants to minimize the energy to do so. The followers, all they do is look at the mean leader trajectory and try to stick with. So in a mean field game context, as the numbers grow very large, we're going to assume there's a fraction of leaders and a fraction of followers, fraction alpha of leaders and 1 minus alpha of followers of the total numbers. And what's going to happen is that these trajectories are going to become deterministic trajectories. So you have to, in the solution, you have to hypothesize two deterministic trajectories other than h of t, which is the target trajectory in like the circle that the sardines want to follow. So we have to hypothesize a trajectory of the leaders and a trajectory of the followers, x bar L of t, x bar F of t. And in terms of these two hypothesized trajectories, write the optimal control law, tracking control law of the leaders, the optimal tracking control law of the followers in terms of these trajectories, and then write that when the leaders average their control laws and the followers average their states under the optimal control laws, they will have to reproduce the trajectories that they assumed in their computations, namely x bar L of t and x bar F of t. So this gives us first linear, of course, dynamics, but two sets of a fixed point equation for the leaders on the one hand, and a fixed point equation for the followers. And the followers also have a different control law. There's a Riccati equation to be solved with a coefficient pi. It's the same for leaders and followers, but what will be different is the offset time-varying function. So let me give you an example simulation, a numerical example of the solution of this problem. Assume we have 200 leaders, 300 followers, and you have some system matrices and some noise coefficients. The reference trajectory is a circle in a two-dimensional plane, and the parametric equations of the circle in x and y are 10 plus 15 sine 2t and 10 plus 20 cosine 2t. This will give you over time a circle centered at 10 in space, a circle. And we are going to assume that the agents or the fish are Gaussian initially with a certain distribution. The red color is for leaders. The blue color is for followers. And now leaders and followers are going to compute their Nash equilibrium control strategy. And let's look at the unfolding of their motion over time. So note that over time, there's going to be a new axis, which is time, and in the xy plane. So when you plot a circle in the xy time trajectory, a circular motion will become helicoidal over time. The circular motion will become helicoidal over time. And so let's see what the optimal, once we carry the optimal control calculations, what the trajectory will look like. Here is an animation of the trajectory. Remember, the red trajectory will look like more or less helicoidal. We're taking 50% weighing for the following trajectory versus the cohesion of the group. The blue line is the mean or the population of followers versus the red line, almost helicoidal, which is the population of the leaders. Okay, so we can look at this simulation one more time. Okay, this animation. So remember, the red is the mean of the red is the leader population. The blue is the follower population. So this huge game is being solved by means of something of order essentially 4, a system of order 4. So it's a huge simplification, of course, in the linear quadratic game framework, and that can be used as a building blocks for other problems which we are about to see in energy systems. So Marilyn, I think at this stage we could perhaps I will stop sharing. So let me well, first I'd like to thank Joanna and Josh for the kind invitation to this session on energy systems. I'll be talking today on the coordination of a large number of thermostatic loads by an aggregator. My co-authors in this work are Quentin Lenné. He did his master's with me and currently works for JP Morgan Chase, and Salman Nazir, who finished his PhD at University of Michigan while I was visiting, and he currently works for Quanta Technology. In the interest of time, I will skip this overview. The motivation for this work is the fact that there's a lot of pressure now for utilities to move towards clean sources of energy, and the most available ones are wind and solar. They're highly intermittent, and so energy storage in that context becomes very important. And the idea is to reach behind the meter towards customers to exploit the existing energy storage attached to loads such as electric water heaters, space heaters, and air conditioners. What are the challenges in doing so if you take a classical centralized approach with one brain sending signals everywhere? There are literally millions of tiny loads that you have to control. There will be severe computation requirements, large communication costs, privacy issues. Past approaches in controlling these loads have been first to send direct control signals to the thermostats. It's currently used, but it has the problem of synchronizing loads as well as sending the same requirements to consumers who may be in very different energy states. More refined approaches have emerged. There's a very large literature by now. We'll cite just a few of those. Centralized approaches where you modulate either duty cycle, set points, fractional on thermostats by Mathieu, Totu, Bashash, and co-authors. And then the second current of research to which we belong, related to mean field and mean field gain-based methods. So mine in 2015 with co-authors used mean field approaches with Markov decision processes. Mine, Kizilkal and co-authors used mean field gain control approaches to these problems. So let's get into this proposed inverse Nash approach. What's the nature of the approach? It's a prescripted game. That is a game where you have the aggregator has the right to define the cost functions of the agents who are the consumers on the other side. Now the objective is to achieve a constant mean power consumption by a collection of loads with whom the aggregator has signed up an agreement. Why do we pick the mean field game context? Because mean field games are do the best when you have very tiny agents asymptotically with zero asymptotic influence, which is the case of these small loads. And then you can use the law of large numbers to achieve maximum predictability and minimize communication requirements. What are the basic steps of our inverse Nash algorithm? First step is to just assume everything goes as planned. That is, the collection of homes consumes on average exactly what you have decreed they should consume as an aggregator. Then select a class of linear quadratic functions with some parameters to be designed. In our case, it's going to be a single time-varying trajectory, a gain, Q of t, a cost gain, the cost function. Step 3, declare that everything, the mean temperature trajectory that you have computed, assuming constant power, corresponds to a mean field gain equilibrium, and reverse engineer the Q of t that will produce this result. So this is really the approach to it. So first you need a model, and we're going to consider a homogeneous population, although this can be easily extended to heterogeneous populations. So the model is a classical thermal shell model with, so a thermal shell losing heat to the environment with a source of heat, which is electric, normally controlled by a thermostat, but we're going to consider that it can be continuously controlled. And therefore, either this means a change in technology or you're dealing with electric heat pumps. Also, there's an internal noise process, which corresponds to random heat gains and heat losses due to customer activity. The cost function is linear quadratic. It has 3 components. The last 2 components correspond to things that favor the customer. For one thing, if Ti represent the temperature inside the home of the ith agent at time t, you'd like that temperature to remain close to the initial value at the beginning of the control. It's considered a desirable state. And also, you'd like the control, the energy, the power that you're using to remain close to the mean power that would have been needed to maintain the energy at x0i. So any deviation from that level is penalized. Now that first term on the left is what the aggregator is going to use to drive the mean of the population, not the mean of individuals, but the population towards a desired level. So it's Qt is a pressure field that will push individual temperatures either towards maximum if you're doing power augmentation, or towards a minimum level tolerable if you're doing low defacement, which is the case we're considering. So Z can be either one of these two values according to your objective. As we said, you have to compute first assuming everything goes as planned, therefore homes are consuming globally the required power level. You're computing what the mean temperature dynamics will be in the mean home. Everything is known here, and therefore it's going to be, the ambient temperature is considered constant, and therefore this is going to be an exponential decay from a mean initial level towards a steady state. Next, given the cost function and an unknown Qt, but you assume if you had it, you write down the tracking problem solution. It's a standard solution. You have an affine feedback. It's linear in the state, and then it depends on the solution of a Riccati equation itself, depending on the Qt trajectory, which is the thing we're trying to compute. And there's also an open loop, which depends on the solution of the Riccati equation trajectory. And it is this open loop control is user specific because it involves the initial condition of the user. We average those equations under closed loop, so we assume everyone closes the loop, and solve for the dynamics of the mean open loop and the mean temperature trajectory. Now the latter, the mean temperature trajectory, is something we know in advance because we're assuming it's going to be the quantity we computed in the previous slide. And then we try to work back the equations that Qt needs to satisfy. Also, in order to solve these equations, they're solved backwards. You need conditions at the end of the interval. We're going to consider the interval is long enough that steady state conditions prevail. That allows us to compute the required boundary conditions at capital T, and we will use them to solve backwards these equations. It turns out that when you manipulate these equations, you can derive the mean of the mean offline trajectory, beta. It will satisfy a Riccati differential equation. And this Riccati differential equation will have guaranteed unique solutions, provided this coefficient here is positive and that coefficient is positive. We can make both coefficients positive, provided we choose appropriately the gain Qx0, the cost function. So now we know we have a unique solution for the offset term. From this offset term, we can work backwards and find what the Riccati equation, or Riccati gain is going to look like, and eventually what Qt is going to look like. So the problem can be solved in this manner, reverse engineer the Qt. We give an example of a simulation of 200 heaters where you're trying to decrease power by 5%. The target power is sent to the users. and they locally compute their control law. They locally compute their control law. This is the obtained trajectories. The red line corresponds to the initial average power in the steady state. Now it is reduced to the yellow line. That's the target. And you can see the empirical average of consumption in homes following that blue line. And if you look at individual trajectories, again, they are decreasing temperatures in the homes, but you can see not all homes contribute the same. The contributions are, the bigger the initial temperature, the more energy there is in the home, the more this home will be solicited through the cost function. So that's an advantage of the approach. With this, I get to my conclusion. So we've developed an inverse MFG approach. It can be applied node-wise in a distribution network, where you would assign to nodes values that would be consistent with the desired aggregate load, but you would modulate those values according to the node sensitivity, node voltage sensitivity, so that you get the flattest load voltage profile. And we'd like to generalize this inverse Nash approach to track more complex aggregate objectives and apply it also to more general control problems. With that, I thank you for your attention.
Well, I guess this concludes, Roland, your presentation. Thank you very much. Very interesting as usual. Let us take time for a couple of questions. So the floor is open for questions to Roland. So, well, I have one actually, Roland. So besides the examples you have presented, can you envision using the midfield game approach to other energy systems? And which ones? We don't hear you.
To other energy systems, what are you thinking about when you say other energy systems? I mean, I'm thinking of storage, essentially, wherever there is storage. So typically, thermal loads are the type that to which you can apply the theory. You could have electric water heaters, for example, also. But of course, you know, I think the methodology has general potential in trying to shape collective dynamics. So for example, traffic or whatever, the idea is using prescriptive game theory. We tend to think of game theory as being adversarial often. But in this case, even if you want to do, if you have one coordinator trying to control the system, it's still useful to think of individuals as being independent decision makers and then act on their cost function. Because ultimately you will get decentralized control laws, and that's very, very important. And these decentralized, so you act locally, but the global result will be the desirable result. Okay, kind of like fish doing things locally, but then the fish school is doing what it's supposed to do. Okay, so that's really the general idea. But of course, the inversion problem, the fact of being able to build a cost function that generates a certain behavior, is not always solvable. It's not necessarily an arbitrary Nash equilibrium dynamics that I can work a cost for. So a class of problems which is interesting is what sort of behaviors can we tailor through these linear quadratic cost functions. You know, that's I think an interesting future research topic, I think.
All right. Yeah.
Okay.
Thank you, Roland. So,
you're welcome.
I have a question, Roland.
Yes, Josh.
A very, very general question.
Yes.
There is a confusion between mean field games where you have leader-follower structure and mean field games where you have what we call main player and other players. Can you say a few words about the distinction between the two, if there is some difference? And if there is some difference, which one is easier to compute?
Okay. So, thank you, George, for your question. The leader-follower in the fifth school, for example, problem, initially, when we studied that problem, I thought we had kind of a Stackelberg, type of situation. But in fact, this is a Nash equilibrium, okay? The leaders are exactly at the same plane as the followers, except that their cost function is different, okay? But they're sitting at the same plane. Whereas, okay, in the major-minor games situation, you could have both. You could have situations where the major is just, although it has a huge influence, but it's still one of the guys, because it's not completely acknowledging its own power. And then you can have a situation where the major agent is really, so the major agent could be uncontrolled for all I know. It could be the weather, completely behaving in a totally independent way, and the like the common noise situation, and the followers could be the thermal loads, let's say. But then you could have a situation where precisely the major agent, aware of its power, will pre-compute, anticipate the reaction, and optimize over that reaction, its own action. So you have the two layers, but in the model I presented, it's a strictly Nash equilibrium. And I would say the Nash is easier to compute, essentially.
Okay, thank you.
You're welcome.
Thank you, George, for the question, and Roland for the answer. We have a question by Farid. Please go ahead.
Hello, Professor.
Hello, Farid.
Thanks a lot for your interesting presentation. I have a question about the inverse Nash equilibrium problem.
Yes.
In your presentation, the goal is that agents track a specific temperature, yeah?
The goal is to have the group mean consumption power be a certain level. Because not everyone follow a specific temperature, but the group lowers its consumption by 5%. It could be more, whatever. So the idea is to assume these are linear dynamics. So you look at the group dynamics, and you send this constant power level to the mean home, and you look at its temperature trajectory starting from the mean initial condition in the homes. That gives you a target trajectory, which you decree is the Nash equilibrium. And then you work backwards the cost function dynamics, Q of t, which would result in this trajectory being a Nash equilibrium. And when you do that, the optimal or the best responses of the agents, they all have the same form in terms of as a law, but their actual behavior is different, because the agents which are initially further from the Z level, which is the lowest tolerable temperature, will be solicited more, will see a bigger error, and will be solicited more than the agents which are closer initially to that. So the pressure field is not the same for everybody, but the mean will still behave. So local actions, but with desired aggregate behavior using prescriptive mean field games, linear quadratic mean field games.
Okay, thanks. Because in a regular mean field game, the agents finally follow the mean of the population.
Yes.
But
this
in
is
the
different.
simulations?
No, this is different.
Oh.
This is different. We want the mean of the population to behave in a certain way, but the agents are not. All the agents are feeling pressure to lower their temperatures, but the pressure is not the same, because the effective pressure is not the same, because they're not equidistant from the bottom temperature that they're being pushed towards. So the ones that are highest have the most energy will give away more than the ones who are colder. And this is what you want, because this is a progressive taxation, so to speak. So the richer will contribute more to the global effort. So that's different from the standard mean field, which is more the agents tracking, like in the fiscal problem where agents are trying to follow a certain mean. That's different. That's navigation objectives, whereas this is more when you're dealing with renewable energies and there's a drop in available renewable energy, you want the load to also respond as a result to lower the consumption. So you want to integrate the load together with the dynamics of the renewable sources.
So if we resume the simulations as you show in your presentation, if we resume the simulation, finally agents reach the steady state power consumption finally or not?
They reach a stable power consumption, but it's not the same for everyone. Okay, it's not, because they have different temperatures when they settle down, and different temperatures means different losses, and the power has to compensate for the losses, the local power. So each one will be consuming at different levels, but the mean consumption will be exactly as planned throughout the horizon.
Great. Thanks a lot, Professor. Thanks.
You're welcome.
Thank you, Farid. Thank you, Roland. I do not see any further questions.
Okay.
So thank you again, Roland, for this very informative presentation, as always.
Thank you very much.
Thank you, everyone, for your participation.
Thanks for your patience, everyone.
And we'll see each other again